Hello everybody and welcome to our today's Learning Connection. My name is Manuel Fischer and I'm the Product Manager for Power Hardware in the Loop testing solutions here at dSPACE. So it's no surprise that I'm today talking about Power Hardware in the Loop, especially in the context of the energy sector. In the following minutes, I'm going to introduce you on the topic Power Hardware in the Loop itself. What is Power Hardware in the Loop? The flexible test method of Power Hardware in the Loop. This will be the topic of my first chapter. After that, I'm going to present you dSPACE's high voltage Power Hardware in the Loop solution, followed by the low voltage Power Hardware in the Loop solution. In the fourth chapter, I'm going to present you the partnerships that we offer for Power Hardware in the Loop. And in the end, I'm going to summarize the overall slides. So, where can we use Power Hardware in the Loop, or where is it necessary to use this flexible test method? In general, testing plays a very important role in the validation process of power electronics in general to prove functionality, such as efficiency, reliability, and you have to make sure that your functions that you're implementing, that they are working. But also safety is a very important reason. If you have safety critical components, you have to make sure that your components work in the context of these safety critical use cases. So some of these tests are only on signal level, or maybe some of them are only valid in a simulation environment, but sometimes it's also necessary to test your components on a voltage, on a power level, so also on high voltage level to get a higher test coverage. A challenge of these test benches, so normally you use mechatronic test benches, rotating test benches with your device on the test machine and the load machine, but the problem is that these test benches are very inflexible towards environment condition, towards changing machine settings and so on. So you have a fixed test bench and it's not possible to change here, for example, machine parameters. I want to give you an example. Here in this picture, in the slide, you see the drivetrain, let's call it drivetrain, of a wind power plant. On the right hand side, you see the wind turbine mechanically connected to a machine, which is here named the generator, which generates our three-phase voltages. These voltages are fed via our device on a test inverter directly to the grid. The problem is we have to test this inverter, and best case is we have to test this inverter in different operating points. So it's very hard to test it in the real environment because we cannot modify, let's say, the wind conditions. For example, if it's a stormy condition or if we have no wind at all. So we have to test it if we want to test it on a power level in the context, for example, with a machine test bench. A load machine is driving our generator. But in that case, we are not flexible enough, for example, to change machine parameters of our generator. The goal of Power Hardware in the Loop now is to embed this device on a test inverter in a fully virtual environment, but with the option that we have the same electric conditions here at the output clamps as they would be available in the real environment. So we have the same currents flowing as they would flow into the grid, as they come from the generator, and that's the task of Power Hardware in the Loop. To give you an overview which test methods are available in general, I want to take this slide with the common V-cycle. Hopefully everybody of you knows this V-cycle with the development path on the left-hand side, and we have the validation path on the right-hand side. The test coverage on the right-hand side increases bottom up, so we start with a software in the loop testing, which is mainly based on simulation tools. So your device under test is simulated in a fully virtual environment. If you want to have a higher test coverage, you can do hardware in the loop testing. That means we read out the output signals of your device under test, calculate in real time which would be the behavior of your environment, and feedback all the signals that normally your environment is feeding back to our device under test, but only on signal level. When it comes to power level, normally mechatronic test benches are used. The same principle as I explained in the slide before. You have your device under test, for example a machine. You have your load machines, so you have a rotating test bed. And with that mechatronic test bench, you can test your device under test on power level with real currents flowing with full electrical power. The last increase, so the highest test coverage, would be bringing your device under test into a real prototype. You see, not only the test coverage increases bottom up, but also the cost increases. Software in the loop only on signal level, only on software level, is a very cheap tool compared to a real prototype. In case of our wind power plant, if you have your real prototype wind power plant, that's a very, very expensive test scenario. Power hardware in the loop closes the gap between our hardware in the loop testing and the mechatronic test benches, because with power hardware in the loop, we have the full flexibility as we have it in hardware in the loop tests to change, for example, some environment parameters via mouse click. But we are now it's now possible to test your device under test at full power level, because we have also the same currents flowing as they would flow in the mechatronic test bench. That's a huge advantage of the power hardware in the loop test method. Further advantages are summarized in the following slides. So we have an improved test coverage compared to signal hardware in the loop, because now we can test on full power level, and we have reduced cost compared to our mechatronic test bench, and especially compared to our real prototype that we had to set up if we do not have power hardware in the loop. We combine the flexibility of hardware in the loop testing at full power. The dSPACE model-based approach of power hardware in the loop brings it two advantages, because you can change model characteristics via model download. So for example, in the first tester setup, you want to emulate your grid, and in the next test setup, you want to emulate your generator, or both of them. And you can also change parameters during the simulation via mouse click. So the first time you test your device on the test with generator A, and then after 10 minutes, you have the possibility with the same setup to test it with generator B by only changing machine settings via mouse click. We do not have any moving parts in these test benches, although we are testing on power level. So compared to rotating test benches, we do not have any moving parts. We do not need the big windmill and your generator. And we do not have any mechanical limitations. So for example, we can have a stepwise change in the speed without any inertia in your generator. That is possible because we simulate in real time your environment and then bring this behavior on the power level. So now I used the words signal hardware in the loop, or only hardware in the loop, and power hardware in the loop. And I want to take the example of our windmill, or our wind power plant, to explain you these two test scenarios. So again, we have our, let's call it drivetrain, or our energy train with the grid on the left-hand side, our device under test, the inverter in the middle of the slide, and our generator mechanically coupled here to our rotor on the right-hand side. When it comes to signal hardware in the loop, especially the control unit of the inverter has to be tested. So the control unit reads the signal, for example, in this case, of current sensors, which are here in the current lines between the inverter and the generator, and between the grid and the inverter, and reads the signals of these currents, compares it with the reference variables for these currents, for example, also reads some mechanical position of the generator, and calculates which firing signals are needed to drive the inverter. When it comes to signal hardware in the loop, for testing the control unit, which is marked here in the red box as device under test, we replace the overall environment by a real-time simulation. But the control unit gets the same signals as it would get from the real environment. So the control unit calculates firing signals. These firing signals are given to a real-time model of our plant. We calculate what is the behavior of this plant in real time and feed back in this case, the current signals, the position signals, so that the control unit on signal level thinks it's in the same environment as in the real world environment. With that approach, we have the possibility to change these parameters via mouse click. It's a very, very flexible, but also reproducible test scenario. So the entire environment is simulated on signal level in real time. And dSPACE has offering of the scalable Scalexio platform. You see here the Scalexio lab box. Scalexio stands more or less for scalable and flexible I/O. You see here the possibility to add many cards. For example, starting with an FPGA card where the real-time model is running. And then you have the possibility to add as many I/O cards as you need for your signal hardware in the loop setup. Okay, but now we want to have the upgrade to also test on power level. And for that, we use power hardware in the loop. Instead of only testing the control unit, now we test the combination of the control unit and the inverter. And now the interfaces, you see it here, are on full power level. Here are currents flowing, and we have to reproduce also these currents. The idea is the same. We replace the environment by a real-time simulation and now add so-called load modules to bring that behavior on the lines, so that at the connecting terminals of the, let's say, of the cabinet, of this power hardware in the loop cabinet, the same electric behavior occurs as it would occur here in the real world plant. So we replace the environment by at least one of these cabinets, and now we reproduce the behavior on the connecting terminals of these lines. So the same currents flow from the virtual generator via the inverter into our virtual grid, and the inverter in combination with the control unit is not able to see, am I connected to the real world generator and grid, or am I connected here to the power hardware in the loop emulation. So again, we have a flexible and reproducible test scenario, but now at full power level. The entire environment is emulated on power level, and we have an improved test coverage compared to only tested on signal level. dSPACE offers not only the Scalexio platform, as we know that from the signal hardware in the loop testing, but also these load modules to bring the behavior to the power level. And in the next slides, I'm going to show you that we also have some kind of power recycling due to the fact that we are not only emulating only the input or the output sides, but both of them. We can circulate the overall power flow. But that I'm going to explain you in one of the next slides. So what you have to keep in mind after this introduction: power hardware in the loop replaces your real world environment by a real-time simulation, and then with the load modules bringing this behavior on the power level with a real-time emulation. We have the full flexibility of changing parameters via mouse click, for example, changing between stormy conditions and conditions with less wind. We can also bring in some failures in the grid. We can bring in harmonic effects to the grid and test if the inverter in this fully bandwidth of different environment condition is still possible to control the overall current flows. That's the big advantage of power hardware in the loop, the full flexibility, but we are at full power level. Now the question is, what do we need for power hardware in the loop? Some of the components I already mentioned. The first component that we need are real-time models. We have to calculate what is the behavior of our environment in real time. For example, in the wind power plant, we need to calculate what is the behavior of the grid, and we have to calculate what is the behavior of our generator. And for that, dSPACE offers open processor and FPGA models. So for tasks which have to be calculated very fast, we use the FPGA technology, especially when it comes to machine emulation. We want to emulate also the current ripple, the triangular waveform, which is forced by the switchboard operation of power electronics devices. So for that, we use the very, very high dynamic FPGA technology. A buzzword, which is also important, is open. We provide you with models of grids, of machines, of battery, for example, but all these models are open. You can use our models, you can parameterize them with your parameters, you can change these parameters, but you also have the flexibility to look behind the curtain, to see all the equations, to change some of the equations, or in some fact you can delete our models and implement your own models with the boundary condition that all these models run in real time. So that is the big advantage of these dSPACE models. You have the full flexibility to set up your own models. We provide you also with some block sets, not only for the processor programming, but also for FPGA programming. All these block sets are based on MATLAB Simulink. The next major component are real-time systems. I already mentioned the Scalexio environment. Real-time system means I need a system which is able to calculate these real-time models in real time. So if I have a very, very slow processor which is not able to run these models in real time, this is not useful for our power hardware in the loop solution. With the Scalexio environment, I have the full flexibility to add exactly these components that I need to run these models in real time. If I need a second processor, just add a second processor board. If I need additional I/O functionalities, just add these functionalities. That's the flexibility of the Scalexio environment. With these two components, we are now able to run signal hardware in the loop tests because I have the real-time models and I have the possibility to bring it on a signal level. When it comes to power level, we have to add the power interface, these so-called electronic load modules. dSPACE offers two types of electronic load modules, a low voltage variant for voltages up to 60 volts and a high voltage variant for output voltages up to 1250 volts. Each of these load modules represents one function. One function could be the phase of a grid, the phase of a machine, the plus or the minus pole of a battery. Each load module is decentrally current controlled, so it only gets the reference currents from our models, from the real-time models. So we can use the same bidirectional load modules for having emulated several functions. For example, if I take 3 load modules, let's run a real-time model of a machine, then these 3 load modules have the behavior of the 3 phases of the machine. When I change the machine model via mouse click, for example, towards a grid model, then exactly the same load modules, 10 minutes later, have the behavior of a grid. That's the full flexibility also seen here on the power side. Due to the fact that each load module is current controlled, we can scale the overall system power by connecting multiple load modules in parallel. So if the power of one load module is not enough, take 2 of them in parallel. Take 10 of them in parallel. There are no limitations in parallelizing these load modules. In total, the overall systems look like this. You see here many of them cabinets. In the cabinets in the middle, all the load modules are placed. So these load modules are here connected in parallel. So this was a setup, for example, that emulates on the one hand a battery. So we have one bunch of modules replacing the plus pole of the battery. We have a couple of load modules replacing the minus pole of the battery. And on the output side, these load modules are replacing a 3-phase machine. So we have many load modules connected in parallel to replace phase 1 of the machine, phase 2, and phase 3 of the machine. On the left-hand side, the cabinet is for the device under test, where the customer can place its device under test. It's customized. You can replace this cabinet by a climate chamber, for example. If the customer has its own housing, you do not need this cabinet, but here's the possibility also to having a housing for your device under test. The uppermost right cabinet is more or less the brain of the overall system. Here's the Scalexio unit placed. So here's where the real-time models are running. We have a high voltage power supply here. We have low voltage power supply, some safety functions like isolation monitoring. But the main part of this cabinet is that all the Scalexio units are placed there and you can run here your real-time models. dSPACE is a one-stop supplier for all these parts. So we can offer you turnkey systems for the overall power hardware in the loop systems. We have the real-time models, we have the real-time hardware, and we have the power interfaces to bring all in your laboratory and set up a turnkey system for your laboratory. The toolchain is seamlessly integrated, so you can start, for example, with these two components to set up signal hardware in the loop testing, and after a few months, if you want to increase your test coverage, you can also add the power interfaces with exactly the same models and exactly the same hardware to bring it also on a power level. And to the fact that we offer open models, you have the full flexibility of bringing in your own ideas towards these models or use our models and only parameterize them. Due to the fact that we have this module-based approach with these load modules, you have also the possibility to upgrade your system at a later point. So for example, if you need more functions, if you want to replace your 3-phase machine by a 6-phase machine, or if you need more power, if you want to double your power, just add the necessary modules. And in case one of these cabinets is fully loaded, just add another cabinet. And after some slides, I'm going to present you the concept of the circulating power flow. In cases we're not only emulating only input and output side, but both of them, we can have a circulating power flow and you only have to feed the power losses. Give me 2 more minutes and I'm going to explain you this principle. Going back to our example, the wind power plant. Our device under test is the inverter in the middle of the grid and our wind generator. This is our real-world setup. Now we want to replace the environment by a power hub in a loop setup. First, we want to replace the real grid. So the grid, in this case the 3-phase grid, will be replaced by at least 3 load modules. These 3 load modules represent the 3 phases of the grid, and I need a real-time model which calculates what is the real-time behavior of my grid. This real-time behavior feeds the reference commands here to these controlled load modules, and now I have grid behavior here at the input clamps of my device under test inverter. The same thing I can do on the right hand side. Instead of having the real-world generator, I replace this real-world generator by also 3 load modules. And to get to know the behavior of these load modules, I need a real-time model of the generator. That's the simply transition between real-world and power hardware in the loop. Due to the fact that all these load modules can be driven bidirectionally and can be used for AC and DC functions, I have the flexibility to cover several use cases. So I can cover testing automated traction inverter that would be having a DC source and an AC sink. Here in the middle is our automotive traction inverter, which is the device under test. We can also test industrial back-to-back inverters by emulating a grid on the left-hand side and a machine or a generator on the right-hand side. Testing chargers is possible with an AC source and a DC sink with a battery. We can also replace it if you want to do it the other way around. For example, if the battery feeds the grid, then we had a DC source and an AC sink. And you can also test DC-DC converters with a DC source and a DC sink. So all the behavior of the load modules depend on the real-time model. The same load modules can be used for several behaviors. If I have a real-time model of a machine, then these load modules have the behavior of one phase of the machine. If I have the real-time model of a grid or a battery, then also my load modules follow exactly these behaviors. Now we come to the slide with the circulating power flow. Again, our example, I have my device under test in the middle. I have 3 load modules representing the grid. The grid model calculates what is grid behavior. On the left-hand side, I have 3 load modules representing the generator with a real-time generator model. And now, due to the fact that I'm not only emulating the input or the output side, but both of them, I can have a circulating power flow. So in case of power coming from the generator, the power is flowing via our device under test towards the grid. And now, due to the fact that all load modules are coupled via a common DC link, we can circulate this power. In an ideal setup, we do not have to feed any power anymore, but in the real world setup, with some losses in our load modules, with some losses in the device under test, I only have to refeed the power losses, which are in the range of 10 up to 15% of the overall system power. That means if you emulate, for example, a 100 kVA system, you only have to feed around about 10 up to 15 kilowatts from the grid. That's especially important if you have your laboratory setup and only have the CE plugs in your laboratory. Do not provide the full power, only feed the power losses. Okay, I talked a lot about these load modules. Now I want to introduce you into these load modules. So as I already told you, each load module is more or less a very high dynamic current sink and source for AC and DC functions. Each load module has a parallel multi-level inverter topology, and that due to the fact that we have multiple branches in parallel, we can reach higher resulting switching frequencies up to 800 kilohertz. These switching frequencies are flexible. So the upper limit are these 800 kilohertz, but if there is no necessity to switch that fast, we can also run these modules at lower switching frequencies. You can use these load modules as sink and as source, and as we saw in the slide before, all these load modules support the power recovery via common DC link. The numbers for the load modules: the maximum output voltage is 1250 volts. That is the limiting factor of the overall system. When it comes to the currents, each load module can cover up to 75 amps RMS for AC functions and 65 amps DC for DC functions per module. If these current values are not enough, just take 2 of them load modules in parallel per function, take 10 of them in parallel per function. There are no limitations. The only limiting factor is the maximum voltage of 1250 volts. So these parallel operations offers you to scale your system via or with respect to the power, also at a later point. So if you start today with a system covering, for example, 100 amps, you can also upgrade the system some months later to 200,000 amps or whatever. So here you have also the flexibility to upgrade your system. Coming again to the overall system, I already explained you this picture. So you see again the device under test housing on the left-hand side. It's also possible to bring in one of our Scalexo lab boxes in the device under test housing. Then you can control the overall test setup via one host PC. So the host PC in this case would not only control our power hardware in the loop test bench, but also the device under test. And yeah, you have the full flexibility to design your device under test cabinet with, for example, measurement equipments like an oscilloscope, cooling water connections, the high power connection, and one traction inverter in this case for device under test. As I explained to you in the slides before, we have the cabinets in the middle with these load modules representing our input and output side for the device under test, and our real-time rack here with the Scalexo units, the high power, high voltage supply. You also see here we have a 400 kVA system, but we only feed with 2 of these small power supply units because we only have to feed the losses. That's one big advantage when you emulate input and output side. So with this setup, you have the highest flexibility at full power level. Highest flexibility towards the models, highest flexibility towards the overall system power by scaling up with different numbers of modules. So you have the highest flexibility at full power level. We offer you a most realistic current emulation, also emulating these, for example, triangular waveforms when it comes to currents driven by a switch mode operated power electronics device. We have an improved test coverage at reduced costs, improved test coverage compared to signal testing, reduced costs compared to mechatronic test benches, and you have a reduction of your development time. So for example, if you want to set up your power electronics device, but the machine, for example, is not available in that early stage of the development process, you can emulate the behavior of your machine if you have the model parameters and test your traction inverter even if your machine is not available at that point. And dSPACE is very experienced with the technology. So our first power hardware in the loop systems were set up 15 years ago. So there's a lot of development effort within these systems. These systems are scalable. So what you see here is a 400 kVA system. If you as a customer ask us for setting up an 800 kVA system, we only add 2 of these load module cabinets. You see we have exactly the same device on the test cabinet on the left-hand side. Instead of 2 cabinets for the load modules, we now have 4 cabinets. And instead of having 2 high voltage power supply units, we need in that case 4. But you can also run the overall system, which is an 800 kVA system with an 125 amps CE plug in your laboratory. That's a very cool environment because we only have to feed the power losses. Okay, I gave you the example of the wind power plant. Now I give you another example, which is predestined because we have this modular approach. So you can also test, for example, let's call it a power management or smart home. In these homes, you have a smart home system which bring all your power and energy functions together. For example, if you have photovoltaics in your rooftop, if you have your grid which supplies you with additional power if photovoltaics are not sufficient, you have consumer loads like heat pumps or whatever. You have a battery storage in your basement where the power from the photovoltaics can be stored. And for example, you have a charger and a wall box. With our flexible approach, you can replace all these functions of the environment also by load modules. So for each function, we implement or we bring in one load module representing the power side. And now we have a real-time model for photovoltaics, a real-time model for grid, consumer loads, and so on. And now you have a test environment for your power management at full power level, but with the full flexibility of saying, okay, per mouse click, now I have fully sun, my car is now charging, I have a storage level or a state of charge of 80%, I have some harmonics in the grid at that point, and the consumer load turns on exactly at that point. So you have the full flexibility of testing all this environment and changing environment settings via mouse click for your power management. That's just an idea how you can use power hardware in a loop when it comes to power management smart home testing. As I told you, you have the full flexibility of changing environment settings. There I also have you some examples when it comes to the generator. You can test if your inverter is also valid to drive the generator when it comes to changes in machine parameters. This is just a theoretical task, but you can test these theoretical tasks on full power level. So for example, if the motor inductance changes from 0.5 millihenry towards 5 millihenry. That was done, you see it here in these measurement results. So in that chart, you see the motor inductance with respect to the time. You see the currents with respect to the time. And you see the quadrature currents, and you see the phase currents here in that chart. You see at the point where the machine in the motor inductance changes, we have here we leave our sinusoidal waveform, and after some seconds or some milliseconds, our controller is able to control again the sinusoidal waveform. But now we know if there comes to some changes, for example, due to some failures, also my traction inverter, or my inverter in general, is able to control these failures. What is also possible, for example, would be changing the machine speed stepwise without any inertia effects. In the real world, not possible, because we have a transition between our, in this case, 1000 RPMs towards the 0 RPMs. With power hardware in the loop, we can change our generator abruptly and double check if our inverter, our grid inverter here in that case, is able also to control these currents that we want, or if this test scenario leads to any problems. That is the full flexibility for power hardware in the loop. Also towards machine parameters, towards grid parameters, we can add up some harmonic effects. That is possible all via mouse click. Now I talked a lot about our high voltage solution. I want to also introduce you towards our low voltage solution. The idea is principle the same. We can use the same module, the same real-time models. We can also use the same real-time hardware, but now instead of having here the interface towards the power with the high voltage modules, we now use the low voltage modules. There's a slight difference between these low voltage modules because each low voltage module can represent 5 functions instead of 1 function. So these modules are set up, for example, for the use case having emulated a battery on the one hand side, so the plus and the minus pole, and a 3-phase machine on the other side. But also with these 5 functions, you can represent these functions that you want to have in your power hardware in the loop. These low voltage power hardware in the loop load modules have included a switched MOSFET stage and have a maximum voltage of 60 volts. Each load module can represent 5 functions, and each function have a maximum current of 50 amps RMS or a peak current of 100 amps for 1 second. Again, also parallel connection of these load modules is supported, so we can also scale the overall system power by connecting many of these load modules in parallel. And we have also the same principle. All functions are connected via a common DC link, so we also support the power recovery. Here in the picture, you see here also many of these load modules connected in parallel to get the overall system power. An exemplary system, in this case it's not for the energy sector, but it was for mild hybrid testing, was the emulation of a 48 volts starter generator PMSN. The overall system has a maximum current of 600 amps RMS and respectively 1200 amps peak, and we have in total 12 of them low voltage load modules connected in parallel. You see these 12 low voltage load modules here, 1, 2, 3, 4, 5, 6, and another 6 here in the second cabinet. You also see our Scalexo units, the brain of the system where the real-time models are running, low voltage power supply units. The customer in that case asked for a failure insertion unit, for example, connecting one of the machine phases hardly to one of the battery poles, the minus pole, for example. So we also customized here this cabinet for the failure insertion unit, and the customer in that case asked also for a climate chamber. So in this case, the ECU, the device under test, is located in the climate chamber. To get all these test scenarios, we have failure insertion unit, and we have the load emulation in these 2 cabinets. Okay, now you're asking, maybe, is dSPACE also doing climate chambers? No, that's not our core competency. I told you we support the overall supply chain with real-time models, real-time hardware, and especially these power modules, but climate chambers are not our core competency. I promised you to give you turnkey systems, so you can ask us also to adding up some climate chambers, but when it comes to a larger laboratory effort, for example, if you want to set up a very, very new laboratory, we have also the possibility to bring in one of our partner companies into the play. We closed partnerships with 2 very, very experienced companies, FEV on the one hand side and IABG on the other hand side. And the use case is that you as a customer has only one single point of contact to get the overall test facility. So a higher aggregated service from one single source. For example, if you're asking for a test bench, dSPACE can do it at your own. But if you're asking for a full laboratory with facility work, for example, bringing cooling water, bringing in a grid connection, bringing in some climate chambers, that would be a part that we can do together with our partners because they are very experienced in the facility work area and we are very, very experienced in these test bench or setting up these test benches. So that is a new offering. We try to bundle these competencies to give you as a customer the full offering for having a turnkey system from one single point. Okay, now I want to summarize this presentation. Within the last minute, I showed you that HIL combines the highest flexibility that we only know from signal hardware-in-the-loop testing. We can change parameters via mouse click. We can change the overall real-time model via mouse click. And HIL combines this behavior with the possibility to bring the behavior at full power level, on a full power level. With the same currents flowing as they will flow into the generator or from the generator to the grid or depending on your use case. We have an outstanding and most realistic current emulation due to the fact that our load modules are very high dynamic and we implemented interfaces between these load modules and our real-time Scalexio systems. So these interfaces are also tuned for having here the real-time behavior. In total, we have very outstanding current emulation. And we have the improved test coverage compared to signal testing and reduced costs compared to mechatronic test benches or, for example, to a prototype. And all of that in a compact system and with the full flexibility of changing the system. So you also have an investment protection. Because if you have 3 load modules, for example, the first day they have a behavior of a machine, and when you change your real-time model, afterwards they have a behavior of a grid. We have a reduction of development time in some cases, because you can test your power electronics devices, even if the environment is not available at that point. And what I already mentioned, power hardware in the loop is a major technology at dSPACE. We are working on that more than 15 years and have a huge experience within this topic. If you are interested in this topic, I can give you 3 links where we have some videos inside. So we have this format called Innovation Coffee Break. In these 2 videos, we have high voltage testing and a charger test done with our demonstrator system, which is located here in Paderborn. Feel free to watch these videos. Then you see one of the systems running in a video format. So not only here on a slide deck, but having a video scene of these systems really, or a real world system of power hardware in a loop running. We also have additional information on our website. And if you have further questions, also feel free to contact me or one of my colleagues. At the end, I want to say thank you for listening. I hope I can give you an idea what power hardware in a loop is and what dSPACE is offering in that topic. Thanks for listening and see you soon.